So types of sections we will see in today's class. So welcome everyone to the week 7 of the live sessions on design of steel structures. I am your TA Danish Bashir from IIT Madras. So in last class we saw compression members, how we have to design the compression members with using merchant Rankine formula. Where I give you the definitions of all the terms. There I also give you the concept of moment of inertia of a section or the radius of gyration. We also studied about the effective length and the slenderness ratio. So how this slenderness ratio is able to control the design of our column. Okay. So in today's class, we will be continuing on where we left last in the last class, and we will be seeing what different things we will be doing. Okay, in today's class. So regarding today's class, we will start with the thing we left in last class. So types of sections. Okay, so types of sections. There can be different types of sections. Okay. Compression member has a very important property, two important properties. Okay, compression member has compression member has two important properties. Okay, two important properties. First is radius of gyration. I am writing it by ROG, radius of gyration, which implies the moment of inertia, because the radius of gyration, moment of inertia is equal to A times radius of gyration का square. Okay, you remember this. Okay, the people. So that's why it's very important. And we know that moment of inertia can be increased. It can be increased if we spread, if we have a same area like this, if we have one section like this and we have the same section like this with the same area cross section, but we are spreading the material. So spreading the material, like we are putting the material here only, we are making it a tube section only. Earlier it was a bar section. Okay, so this was having whole material, this is confined to one place. Okay, so this we have spread it on all the four directions. So yeah, spreading the material away from the axis of this away from the axis makes the compression member very ideal. Okay, so there is one more definition about the ideal compression member. Okay, so ideal section, an ideal section is one which has a same moment of inertia about any axis through its center of gravity. So it is center of gravity. Okay, so it is an ideal section. Rolled steel section cost less than built-up sections per unit weight and use. Rods bars withstand very little compression with length when length is more. We know that. Tubular sections are more suitable for small loads and lengths. These sections are usually provided for roof trusses and bracings. Okay, we have different types of sections like rolled steel sections. We have rolled steel sections. We have built-up sections. Okay. Okay, we have build up sections also. We have rods and bars. Okay, we have there. We have tubular sections. Okay, these sections are usually provided for roof trusses and bracings. Okay, trusses and bracings. Okay, we provided for roof trusses and bracings. Okay, the use of tubes as compression members was limited over decades due to the difficulty of making connections with the riveted and bolts. But with the development of welding techniques, it used to become frequent for the following reasons. Okay, tubes are also used as compression members because of the following reasons. Okay, first, tubes have same radius of gyration in all the directions and have high local buckling strength. Okay, same radius of gyration in all directions. It is there. It has same radius of gyration in all directions and a high local. A high local buckling strength. Okay, high local buckling strength. One more thing, you might have studied in mechanics of materials that tubular sections have more torsional resistance than built-up sections, solid sections. Okay, so another case is tubes have more torsional resistance. Resistance than solid sections. Okay, that's why we are using tubular sections. In case of members subject to the wind, round tubes are subject to less force than flat sections. Okay, so third case is in case of members subject to wind. Okay, round tubes are subjected to less force than flat sections. For flat sections. Okay, this is there. So we can see different types of built-up sections. Like built-up sections here, we have joined two angle sections here. Like in this manner, two angle sections are joined in this manner. Or like this and this, we will join them with bracings. Like we can put these angle sections here. Like we can put this and this, we can put this and this here. And we can put this, we can make a full built-up section here. Similarly, this, we can join it by this. We can join it by this, okay? There are different combinations. You can see that. We can make a plate girder like this. This is one plate, this is one plate, this is one plate. This is angle section, angle selection, angle section. We made a whole eye section using plates, okay? These are the different types of sections that we use, okay? There we have one important thing. It is buckling, okay? So what do we mean by buckling? So when an actually loaded compression member becomes unstable overall, uh, that is not locally unstable, it can buckle in one of the following three ways. Okay, so when we load our, for example, this is our compression member. Okay, when we load in this direction, it becomes unstable, globally unstable. Okay, then we call this type of instability as buckling. So this is actually a geometric instability that happens in our columns. It can have many reasons, like if the slenderness ratio is very large, that is, it's having very thin core, so it can buckle. In those cases, it can buckle. There are another lot of reasons in which a column can buckle. Okay, so what are the different types in which a column can buckle? Is first is the flexural buckling. What do we mean by flexural buckling? Is it is a deflection caused by the bending or flexure about the axis corresponding to the largest slenderness ratio. Okay, whatever will be the largest slenderness ratio along whichever axis, if the column bends along this bends along that axis, that we call as flexural buckling. This is usually the minor principal axis, the one with the smallest radius of gyration. Obviously, lambda will is inversely proportional to 1 by radius of gyration. So whatever will be the minor principal axis, along that axis column will buckle, and it will be along the smallest radius of gyration. Compression members with any type of cross-sectional configuration tail in this way. Okay, this can be the mode of failure. Then another can be torsional buckling. The flexural buckling connected above is the bending alone. That is the section displaced from the original position by translation without rotation. Okay. Thin walled members with open cross-sectional shape or sometimes weak in torsion and hence may buckle by twisting rather than bending. Torsional buckling occurs when the torsional rigidity of the member is appreciably small. So we saw that in flexural buckling. What happens in flexural buckling? It buckles due to the translation of a member from its original axis along. This flexural buckling usually happens along the direction in which the slenderness ratio is maximum. That is, if the slenderness ratio is maximum, its radius of gyration will be minimum. So whatever will be the thinner side of the column will buckle in that direction or it will bend along that direction. Another case is torsional buckling. Torsional buckling, this torsional buckling, like in unlike the flexural buckling in which it bends, in torsional buckling, it rotates. Here the member rotates. This is because this usually happens. This is very uncommon in solid sections, but when we use hollow sections like tube sections, distortional buckling will be there. This is because these sections have very less or smaller torsional rigidity. Well, the torsional rigidity is very less. These columns buckle in torsional mode. Okay. Then there can be the combination of these both two bucklings. Okay. These can occur in a mixed mode, that is torsional buckling and flexural buckling. This type of failure is caused by the combination of flexural buckling and torsional buckling. The member bends and twists simultaneously. This type of failure can occur only with the unsymmetrical cross sections, both those with one axis of symmetry. Okay, it is there. Then we have design of actually loaded compression members. Okay, we will study that and we will follow a numerical problem after that. Okay. We have design of actually loaded columns. Okay. So for the design of actually loaded columns, what are the different assumptions that we have to make? The idle column section is assumed to be absolutely straight, having no crookedness, whichever occur in the practice. The modulus of elasticity is assumed to be constant in build-up section. Okay. Secondary stresses, which may be of the order of even 25 to 40% of the primary stresses, are neglected, like the other stresses. Okay. Then we will directly go to one numerical problem. So what is that? Calculate the value of the least radius of gyration of the compound column consisting of Indian standard high beam ISHB, which is having a unit weight of 250, ISHB 250 at a weight of 536.6 Newton per meter, with a cover plates of 300 mm cross 20 mm on each flange. So this is 300 mm, this is 300 mm, this is 20 mm in thickness, and we have ISHB. Okay. So you have to keep IS handbook with you so as to follow these type of numericals. Okay. So first of all, we will refer to this pic. Okay. Everything is shown in this figure. Okay. Then we will write different things. So we have ISHB section. Okay. So ISHB section 250. So from IS handbook, it is IXX is calculated to be equal to 798 3.9 into 10 power 4 mm power 4. This is there, and its gross area of cross section is 6971 mm square. Okay, we keep this in mind. Okay, one more thing, IXX, about this axis. Okay, about this axis of plates, uh, for plates. Okay, because we are calculating the total moment of inertia of the whole section will be since there are two plates, we have to see the moment of inertia of the plate along AA axis, along this axis. Okay, it will be its centroidal axis, and then we have a distance this between the x-axis and AA axis, so it will be by the parallel axis theorem plus area of plate. Okay, AP times y1 square. Okay, AP times y1 square. It will be there. Okay. When we plug in all the values twice, IAA will be BDQ by 12. Okay. B it is 300. Okay. 300. D is 20. Depth is 20 Q by 12. Okay. This is there. Plus AP is what is AP? This is 300 times 20. This is the area of the cross section Y1. How much it is the Y1? It is half of 250. Okay. Okay, it will be 125 plus 10 half of this. Okay, over whole square. Once we will calculate this, we will get IXX for plates to be equal to 21910 into 10 power 4 mm power 4. Okay, this is the whole. So total IXX will be equal to, total IXX of the section will be equal to 7,983.9 plus 21910 into 10 power 4 mm power 4. Okay, total IXX comes out to be 29893.9 into 10 power 4 mm power 4. Okay, what is the total area of cross section? Area of cross section will be the summation of the two area of cross, all the cross sections. 6971 is the for ISHB, plus two plates are there. Their area is 300 times 20. Okay, it comes out to be 189071 mm square. Okay, now what is the definition of the radius of gyration? So the radius of gyration is given as Rxx, comes out to be Ixx by A. So Ixx is 29893.9 in 10 power 4 divided by 18971. 18971. It comes out to be 125.52 mm is the radius of gyration of this section. Okay. This is along Ixx. We have to calculate what we have to calculate the value of least radius of gyration. So we check it along x-axis, we will check along y-axis. So IYY for ISHB. Again, from the handbook book, it is given as 2011.7 into 10 power 4 mm power 4. Okay, for IYY for plates. Okay, these are two plates, so we have 2 times IYY. Okay, so YY axis is passing throughout their centroid, so it will be BDQ by 12. So B will be 20 now, and D will be 300. Okay, it's reverse by 12. Okay, it comes out to be 9000 mm power 4. Okay, okay, these are the different things there. Okay, 9000 mm power 4. So total IYY along total IYY will be total IYY will be 2011.7 plus 9000. Okay, 10 power 4. Okay, it comes out to be IYY comes out to be 11011.7 into 10 power 4 mm power 4. Okay, so area of cross section will be same, or YY comes out to be IYY divided by A. It comes out to be 11,011.7 into 10 power 4 divided by area of cross section is 18971, or YY comes out to be 76.187 mm. So the least radius of gyration is RYY. Okay. I hope you got this point. This is a very basic numerical. You might be asked this numerical in your examination. Then we have one more example. Okay. We have we have calculated the safe actual load for a stanchion ISHB 350 at the rate of 710.2 Newton per meter. 3.5 meter is high. It is to be used as an uncased column in a single story building. The column is restrained in direction and position at both ends, and Fy to be equal to 250 Newton per mm square. So let us follow this. Okay. So since it is restrained in direction and position from both sides. So what will be the effective length? L will be 65% of its length. Okay, 65% of its total length. It comes out to be 0.65. It is 3.5 mm, 3.5 meter high. It is 3500 meter, 3500 mm. Okay, it comes out to be 2275 mm. It is effective length. Okay, so from IS handbook number 1, on what are the relevant properties of ISHB 350 at the rate Newton per mm. What are the relevant properties? It's Rxx radius of gyration along the x-axis is 146.5 mm. What is R? Y is 52.2 mm, and gross area of cross section is 9221 mm square. Okay, these are the properties from there. So minimum radius of gyration is this. Okay, minimum radius of gyration is this. So it is slenderness ratio. Lambda is equal to L by, or it will be L by or YY. If you divide 2275 divided by 52.2, it comes out to be 43.58 as slenderness ratio. So if you look at the code for L by R equal to 43.58 and Fy equal to 250 Newton per mm square, you will find that allowable compressive stress sigma AC is equal to 136.49 Newton per mm square. So we got the allowable compressive stress. So we can easily get allowable this safe action load. Okay. Therefore, safe action load. Okay. Load will be equal to sigma AC multiplied by area of cross section. Sigma AC comes out to be 1360.49 Newton per mm square divided by 9221 mm square. It comes out to be 125857.4.29 Newton. It is 12058.57 kilonewton. Safe actual load. P safe. Okay. So there is one more numerical. It is a compound section. I expect you people to try it at your places. Okay. Thank you everyone for joining. Okay.